Okay. Hi everyone, welcome to this live stream. This video will be starting the new Windows Server 2025. So I just want to share my screen. Network Fundamentals and Introduction to Windows Server 2025. In this chapter, we established a foundation for your journey into Windows Server 2025. Understanding the fundamentals is crucial. So let's get started. We begin by exploring the essential of computer networks. Imagining a bustling city of interconnected roads, devices, hosts communicate with each other via these pathways. We will delve into the concepts such as hosts, nodes, client-server architecture, and other network components. Additionally, we demystify IP addressing and subnetting, which function like the postal codes of the digital world. Next, we shift our focus to the network operating system, NOS. Think of the NOS as the conductor of our network orchestra. We will discuss the hardware and software requirements for running a server. Furthermore, we will take an in-depth look at Windows Server 2025 itself, its additions, its improvements over Windows Server 2022, and exciting new features. Imagine enhanced security protocols, seamless hybrid cloud integration, and cutting-edge technical support, all part of the Windows Server 2025 symphony. Ready to roll up your sleeves. We will cover the detailed system requirements for Windows Server 2025. Additionally, this chapter will guide you through downloading and preparing the installation media. Consider it your backstage pass to server greatness. Finally, we will equip you with practical skills you can download and install Windows Server 2025 Trusty Sidekick Windows Admin Center. This tool will be your companion as we venture into more advanced topics in the upcoming chapters. By the end of this chapter, you will have a solid grasp of networking principles, NOS principles, and the specifics of Windows Server 2025. Buckle up, it's a transformative journey that will lead you to mastering Windows Server management in today's dynamic IT landscape. In this chapter, we're going to cover the following main topics: understanding hosts, nodes, and client-server architecture, overview of IP addressing and subnetting, getting to know the server, understanding network operating system, overview and additions of Windows Server 2025, key differences between Windows Server 2025 and Windows Server 2022, minimum and recommended system requirements for Windows Server 2025, downloading Windows Server 2025 and Windows Admin Center. Technical requirements. So to complete the exercise in this chapter, ensure your PC is running a Windows 11 Pro equipped with a minimum of 8 gigs of RAM, 500 meg of available disk space, and an active internet connection. Understanding hosts, nodes, and client-server architecture. As you embark on this section, you might initially question the relevance of learning about computer networking when your primary interest lies in Windows Server. This concern is valid at first. However, as you progress deeper into the realm of Windows Server, you will increasingly recognize the importance of a solid understanding of computer networks. This chapter covers foundational concepts such as IP addressing, subnetting, and network components that are integral to effectively managing server environments. By understanding these basics, you'll gain the context you need to approach Windows Server tasks with confidence, making it easier to handle real-world configurations and troubleshooting down the line. While this book will focus on Windows Server, these networking principles serve as the backbone of every server environment, giving you the tools to navigate server management with precision. To grasp the significance of computer networks, let us revisit these origins. The necessity for resource sharing sparked the initial development of networking technologies. many years ago during the 1960s and 1970s. As demand grew, so did the advancements of these technologies, leading to the creation of comprehensive terms and concepts essential for describing computer networks. Thus, terms such as network types, topologies, architectures, and components emerged, marking computer networks as one of humanity's monumental communication innovations. The internet exemplifies the profound social benefits of computer networks, connecting countless computers and bridging geographical distances in communication. So, what is a computer network? According to the Merriam-Webster dictionary, a network is defined as a group of people or organizations that are closely linked and work with each other. Additionally, networking is described as the exchange of information or services among individuals, groups, or institutions. These definitions provide a simple, concrete basis for understanding computer networks. In essence, a computer network is a group of computers connected through networking devices and media to share resources. These resources typically include network services and peripheral devices. For instance, sharing files, applications, printers, and other peripherals is straightforward in a networked environment. It is essential to distinguish between what a computer network is and what it does. The former explains the structure and components, while the latter highlights the benefits and functionalities. You can see here in figure 1.1 illustrates that a computer network comprises interconnected computers sharing resources. Computer networks come in various types, each serving different purposes and covering other areas. Let us explore these types individually. Types of computer networks. Designing and building a computer network is a fascinating process closely tied to its definition. At its core, a computer network requires at least two computers. The number of computers and how they access shared resources determines the categorization of network types, which will be detailed in the following sections. Generally, computer networks are categorized based on the area they cover and their intended purpose. We will discuss some of the most common types of computer networks here. So, personal area networks. A personal area network, PAN, depicted in figure 1.2, connects and transmits data among devices within a private area, typically belonging to an individual. For example, in your home office, your laptop, smartphone, printer, and headphones might all be connected via Bluetooth or Wi-Fi, often referred to as a home area network, HAN. A PAN uses technologies such as Bluetooth and Wi-Fi to interconnect devices. Another type of network is the local area network, LAN, which has a much more extensive coverage area compared to a PAN. Let us explore this in the next section. So, local area network. A LAN connects two or more computers within a local area, such as a single room, a floor, several floors, a building, or multiple adjacent buildings. LANs typically use a central device and networking media such as twisted pair, coaxial, or fiber optic cables to interconnect computers. Figure 1.3 illustrates an extended LAN that utilizes two switches to connect multiple devices. This configuration enhances network capacity and allows for greater scalability by enabling communication across different segments of the network. The use of multiple switches in the extended LAN ensures efficient data transfer between devices, improving all performance and reliability. This setup is commonly used in larger environments to accommodate growing network demands while maintaining optimal performance and minimum latency. Furthermore, comparing PANs and LANs, a PAN is primarily dominated by portable devices such as smartphones, while a LAN mainly consists of fixed devices. Both cover local area, but a LAN has a broader range, potentially spanning an entire building or multiple buildings. A PAN is organized around an individual, where a LAN is organized around a specific site. So you can see here, here's a picture of a LAN, which are 6 computers, and in the middle then is a switch. The next type of network we'll examine is the metropolitan area network, MAN, which has even more excellent coverage than a LAN. A MAN illustrated in figure 1.4 connects multiple LANs within a town or city. MANs exist to facilitate resource sharing and access within a metropolitan area. They offer more excellent coverage than LANs, but less than wide area networks, WANs. MANs are faster than both LANs and WANs, often using fiber optics and gigabit layer 3 switches for high-speed interconnection. Finally, we understand WANs, which have the most significant coverage, wide area network. A WAN depicted in figure 1.5 covers extensive geographic areas beyond the reach of LANs and MANs. WANs use dedicated telecommunication lines such as telephone lines, lease lines, or satellite, making them accessible from geographic locations. The internet is a quasi-essential example of a WAN. So understanding computer network components, just as personal computers, PCs, have their components. Computer networks also consist of essential elements. While PCs and peripheral devices are familiar to most people, IT professionals focus on components such as networking devices, network media, and NOS. First, let us clarify the roles of clients and servers within a computer network. Understanding clients and servers. In the context of a computer network, clients and servers revolve around accessing and providing network resources. Clients typically initiate requests for resources, while servers are responsible for delivering and managing access to these resources. Both play vital roles in network operations. For instance, as depicted in figure 1.6, a server connected directly to a printer offers printing services to PCs acting as print requesters. Although clients and servers are fundamentally network components, their roles are defined differently in network terminology. Let's explore how they fit into the broader network structure. Understanding hosts and nodes. Have you ever come across the terms such as hosts and nodes and wondered about their distinctions? While they may initially seem similar, hosts and node serve distinct purposes in network communication. All hosts can be considered nodes, but not every node functions as a host. A host refers to any device with an assigned IP address on its network interface actively requesting or providing networking services. Typically, clients, servers, and routers operate as hosts. On the other hand, a node is any device capable of receiving and transmitting network services but lacks an IP address assignment on its interface. Nodes typically have network interfaces used for management purposes. For example, in figure 1.7, PCs and the file server act as hosts while switches function as nodes. In a Windows Server environment, understanding the distinction between hosts and nodes is essential. Windows Server frequently operates in a client-server model. In this world, the server provides resources and the client devices connect to access these services. This setup supports effective resource distribution across networks and is fundamental to IT administration. As you may know, switches operate by forwarding frames within a local network, ensuring data is efficiently transmitted between network devices on the same network segment. In contrast, routers are responsible for forwarding packets across different networks, enabling communication between separate network segments. or even across the internet. Both switches and routers play critical roles in network infrastructure, with switches focusing on local traffic management and routers handling more complex inter-network routing to ensure seamless connectivity. Understanding the distinction between these two devices is fundamental for effective network design and troubleshooting. Now that we understand a network and its essential components, we can explore network architectures. Understanding computer network architectures. Discussions about computer networks often involve exploring fundamental and overarching concepts such as the components that comprise them. That includes considerations of network types based on coverage areas and physical and logical topologies govern their physical layout and structural organization. Computer network architecture encompasses a comprehensive framework that integrates elements as such as physical and logical topologies, network components, communication protocols, and operational principles. Moreover, computer network architecture serves as a design framework enabling computers to communicate using a request and response paradigm. The most prevalent network architectures include a peer-to-peer and client server models. So let us begin by exploring the P2P network architecture. In the P2P network, as illustrated in Figure 1.8, hosts operate without predefined roles. Instead, they dynamically switch roles between the client and server based on their current network activities. For instance, if PC1 requests services from PC2, PC1 acts as the client while PC2 serves as the server. Conventionally, if PC2 initiates a request to PC1, PC2 becomes the client and PC1 the server. PANs often exemplify P2P network setups. Client-server network architecture. In contrast, a client-server network architecture presented earlier in Figure 1.7 designates specific roles to hosts. Clients are devices that request services, while servers are devices that provide services within the network. This structured approach to networking ensures efficient operations by clearly defining the roles of each device. Typically, client and server responsibilities are designated to specific machines, allowing for streamlined communication and resource management across the network. This architecture is foundational in many enterprise environments where scalability and reliability are crucial. Each component of networking, from hosts and nodes to client-server architecture, directly supports your work within Windows Server 2025, whether configuring access permissions, setting up resource sharing, or monitoring network traffic. These concepts will reoccur throughout your server management tasks. With a clearer understanding of network operations, the next section will delve into the fundamental requirements for computers to communicate within a network, the IP address. In order for computers to effectively communicate within a network, an IP address is required, serving as its unique identifier on that network. Think of an IP address as a device's unique identifier, similar to a postal address. In server management, IP addressing enables you to define the network structure and configure devices to communicate efficiently within and across networks. In more complex networks, subnetting is used to define specific segments within the larger network structure, dividing it into smaller, more manageable parts. This segmentation enhances both security and performance. Two key factors when managing Windows Server environments where maintaining streamlined communication and data flow is essential. Currently, two leading IP addressing technologies are recognized globally: IPv4 and IPv6. Despite the increasing prominence of IPv6, IPv4 remains the predominant addressing standard in internet traffic. Let us begin by examining IPv4 addresses. IPv4, or Internet Protocol version 4, assigns addresses consisting of 32 bits organized into 4 octets separated with dots for readability, e.g. 192.168.1.1. The destination v4 denotes the fourth iteration of IP addressing specified in IETF publication RFC 791. IPv4 addresses are characterized into classes A, B, C, D, and E based on their initial octet ranges as shown in Table 1.1. So IPv4 classes, the IPv4 range of the first octet: A, 1 to 127, B, 128 to 191, C, 192 to 223, D, 224 to 239, E, 240 to 255. As you progress through this chapter, you may encounter areas that require further clarification. Essentially, if you are new to IT, to address these challenges, it is crucial to focus on practical applications of the concepts discussed. Understanding how these foundational networking principles directly apply to Windows Server management will enhance your learning experience. Now let us explore the IPv6 addressing technology that was introduced to address the exhaustion of IPv4 network addresses. IPv6, or Internet Protocol version 6, was designed to overcome the limitations posed by the exhaustion of IPv4 addresses, which are only 32 bits in length and provide around 4.3 billion unique addresses. In contrast, IPv6 employs a 128-bit address format, allowing for an astronomical total of approximately 340 undecimal unique addresses as specified in IETF RFC 2460. The vast address space is represented in hexadecimal notation and segmented by colons, exemplified by addresses such as you can see here. The implementation of IPv6 not only provides an extensive range of addresses, but also includes several features that enhance network efficiency and security. For instance, IPv6 supports auto configuration, enabling devices to generate their IP addresses without the need for a DHCP server. That is particularly beneficial in dynamic environments where devices frequently connect and disconnect, such as in Internet of Things applications, IoT. Additionally, IPv6 incorporates built-in security features such as IPsec, which provides end-to-end encryption and authentication, further safeguarding data transmission across networks. To illustrate the practical benefits of IPv6, consider a smart home setup that includes various connected devices such as smart thermostats, lights, and security cameras. With the extensive address space of each IPv6, each device can have a unique IP address, allowing for seamless communication and management without the complexities of address translation or the risk of address conflicts inherent in IPv4 networks. Furthermore, the ability to use multicast addressing in IPv6 facilitates efficient data disruption, such as streaming video to multiple devices simultaneously without requiring multiple unicast streams. IPv6 not only resolves IPv4's address scarcity, but also introduces significant advancements that improve network management, security, and scalability, making it a vital evolution in internet architecture as the number of connected devices continue to soar. So next we'll delve into IPv4 subnetting, which plays a crucial role in identifying network addresses. So I'm going to leave it here this evening for this stream. Thank you for listening and have a nice weekend.